What if we could scoop up every last ray from a star, harness its colossal power, and bend it to our will? Picture an object so vast it outshines planetary ambitions. This isn't fantasy, it's the dream of the Dyson Sphere. In 1960, physicist Freeman Dyson looked at Earth's growing energy needs and asked a simple question. If a civilization grows unchecked, how will it find new power? His answer, albeit speculative, was breathtaking. Build a swarm of collectors around your star. Not a rigid shell, not a solitary structure, but trillions of orbiting satellites soaking up sunlight like cosmic sunflowers. This wasn't a formal proposal. It was a thought experiment and invitation to push our imagination beyond earthbound limits. Dyson's insight transformed the search for extraterrestrial life. Instead of scanning radio waves alone, maybe we should hunt for the infrared glow of star-encompassing machinery. Let's talk numbers. A modern solar farm might cover 10 square kilometers to power a small city. Move to Mars, and you double that, still peanuts on a cosmic scale. A full Dyson swarm. You're looking at quintillions of square kilometers. To wrap the sun in collectors, you'd need surface area far exceeding all planets combined. Pause here. Let that sink in. Every molecule in our solar system barely scratches the material budget for just a fraction of this megastructure. We're talking about engineering feats that dwarf every human project in history. Multiplied by factors we struggle even to pronounce. Visionaries haven't stopped at Dyson's original swarm concept. They've dreamed up radical twists. Solid shell, a continuous shell at 1 astronomical unit. Pros: complete envelopment, uniform energy capture. Cons: gravitational collapse, impossible structural stresses. Dyson swarm: myriad independent satellites in orbits. Pros: incremental construction, modular maintenance. Cons: collision risks, complex coordination. Dyson bubble: statites held by solar sail pressure, hovering in place. Pros: no orbital decay. Cons: sails vulnerable to micrometeoroids, requires perfect attitude control. Beyond these, sci-fi icons like Larry Niven imagined ringworlds a-ring encircling a star's habitable zone, and Alderson disks giant flat disks spanning planetary orbits. Each option balances risk, reward, and staggering imagination. Where to find the raw materials? Option 1. Dismantle Mercury. At 3.3 times 10 to the 23rd kilograms, it's rich in metals iron, nickel, chromium. Option 2. Send swarms of mining bots to the asteroid belt. These rocky bodies are a goldmine of silicates, carbon, even water ice for fuel and life support. Option 3. Tap into the moons of Jupiter and Saturn. Think Deimos and Phobos as shuttles, Europa's ice for hydrogen. Each source poses challenges. Transportation time years for remote targets. Autonomous mining technology requiring self-replication. Ethical questions: should we strip mine celestial bodies without knowing their ecosystems? We'd need fleets of robotic factories, self-replicating machines that turn raw rock into solar collectors 10,000 kilometers wide. Construction demands breakthroughs in multiple fields: materials, science, ultralight, radiation-resistant alloys, metamaterials to focus and funnel light, robotics and AI, self-replicating robots that mine, process, assemble, swarm intelligence for coordination of trillions of units, orbit dynamics, collision avoidance algorithms rivaling global air traffic control, active station keeping to counter solar wind and gravitational perturbations. Imagine orbital shipyards the size of moons, powered by local energy, churning out collectors at astonishing rates. Each collector is a microcosm of automation, from power generation to health diagnostics and repair. Harvesting energy is only half the battle. You must transmit it. Laser beaming: pros: high directionality, efficient. Cons: requires perfect alignment, atmospheric interference. Microwave transmission: pros: proven on Earth at smaller scales. Cons: large transmitting and receiving arrays, waste heat, A network of relay satellites could form a phased array, beaming power precisely where it's needed to Earth, Mars, orbital habitats, or deep space shipyards. But guard against signal degradation, interference, and the potential weaponization of focused energy beams. With a Dyson-level reservoir of power, civilization leaps to Type 2 on the Kardashev scale. We unlock possibilities. Matryoshka brains, nested layers of collectors. Powering supercomputers, running digital civilizations. Interstellar travel, laser-pushed light sails, accelerating crafts to relativistic speeds, terraforming at scale. Reviving barren worlds across multiple star systems. But this power demands wisdom. A Type 2 Mistapanchik expansion or weaponization could spell cosmic catastrophe. Stewardship becomes the civilization's greatest challenge. If aliens built Dyson spheres, we might see them. Astronomers search for infrared excess, stars radiating more heat than light signaling, energy, reprocessing. Transit anomalies, irregular dimming events like Tabby star, hinting at orbiting megastructures. Spectral signatures, unusual absorption lines from industrial materials. Projects like Breakthrough Listen, WISE infrared surveys, and future telescopes keep scanning. So far, no conclusive evidence, but the search has just begun. Questions arise. Do we have the right to reshape our star system? Imperialism of the cosmos. Are we repeating terrestrial colonial mistakes on a solar scale? Preservation of natural beauty? Does biodiversity extend to barren moons and asteroids? Long-term risks. A Dyson sphere gone rogue could trap a star's heat, destabilize orbits, or fracture under stress. Yet, the alternative energy scarcity may condemn future generations to turmoil. Perhaps the greatest moral imperative is to ensure survival and flourishing, even if it means radical cosmic engineering. Building a Dyson sphere might feel like a dream for a civilization centuries or millennia ahead. But every solar panel we deploy, every asteroid we explore, every advance in robotics and fusion power nudges us closer to that cosmic frontier. What if we dared to dream bigger? What if capturing a star's light becomes our legacy? Let's keep asking how far we can go and then dare to go even further. Smash that subscribe button, share your wildest structure ideas in the comments, and together we'll chart our path among the stars. Bonus deep dives, Matryoshka brains. How nested shells maximize computing power. Shelling points, using game theory to coordinate decentralized swarms. Exotic variants, Niven rings, Alderson disks, and the ultimate hive mind nexus. SETI strategies. Building telescopes to detect stellar engineering across the cosmos. Brace yourself for our next video. We might tackle ring world physics or the mysteries of interstellar arc ships. Until then, keep looking up.